Let's take a look at one more example from section 4.5. Let's solve the differential equation y double prime plus y equals x cosine x minus cosine x. We'll start off the same way we've been doing. We want to find the complementary solution first, so let's find y sub c. We need to solve the homogeneous differential equation y double prime plus y equals to 0. We get the auxiliary equation m squared plus 1 equals to 0. Take the negative 1 to the other side, take the square root. We're going to come up with m equals plus or minus I. So it's a complex solution. So we know that our solution is going to be of the form e to the alpha times c1 cosine beta x plus c2 sine beta x. Alpha is 0, beta is 1. So our solution is going to be the following. So we have yc equals c1 cosine x plus c2 sine x. The next thing we want to now do is we want to find a differential operator to annihilate the function g of x. So step 2, we're going to find yp, find the particular solution. So we have x cosine x and minus cosine x. And this is in the notes. This is the image I uploaded in D2L. But the operator is d squared minus 2 alpha d, looks like a b, plus alpha squared plus beta squared, whole thing raised to the n power. That will annihilate both of these terms. There is no exponential part, so the alpha is 0. And remember, the n itself comes from 1 more than the highest power of x that would be in front of any of these. So the n is going to be 2. And the beta, forgot to include beta here, but beta would be the argument of the trig functions. Since it's the cosine of x, that's 1x, so beta is equal to 1. So this differential operator here is going to be d squared. If alpha is 0, then this part doesn't show up. That part doesn't show up. Beta is 1. 1 squared is 1. And then it's going to be to the second power. So the operator d squared plus 1 squared, that is going to annihilate x cosine x minus cosine x. So what we're now going to do is we're going to apply that differential operator to both sides. And before I do so, let's go ahead and write our differential equation operator format. Y double prime plus y, that would be d squared plus 1 applied to the function y is equal to x cosine x minus cosine x. And we're now applying our annihilator operator, which is d squared plus 1 squared. D squared plus 1 squared. On the right hand side, we know that that's going to be equal to 0. So we get a homogeneous differential equation. And it just so turns out that these two are the same factor. So we end up with d squared plus 1 cubed applied to y equals to 0. We can now solve this homogeneous differential equation by considering the auxiliary equation m squared plus 1 cubed equals to 0. That is m squared plus 1 times m squared plus 1 times m squared plus 1 equals to 0. And we know that the roots from previously, the roots of this are going to be plus or minus I, where each of those is going to be of order 3. Okay. So each one of those is going to be of order 3. So what that means for the solution here, let's come up here and write it. and maybe I'll eliminate a lot more because we're going to need some space. So if we had I, plus or minus I, we know that that would give us a C1 cosine x plus C1 sine x. But because it appears of order 3, we're also going to get an x times each of those. So we're going to get C1x cosine x, not C1, we already used C1. C3x cosine x plus C4x sine x plus another x. We're going to have C5x squared cosine x plus C6 x squared sine x. So this is kind of what the overall general solution is going to end up looking like. Now, some of this is shared with the complementary solution. If we look at the C1 cosine x sine x, that was already a part of the complementary solution, which means that whatever's left over, it's those terms that would form the particular solution. And I'm going to, again, kind of not write the C3, C4. I'll switch over to some easier letters to work with. But now we need to find the undetermined coefficients for our particular solution. So we assume that y sub p has the form, I'll call it ax plus cosine x plus bx sine x plus, again, skip d, that's our differential operator. We'll call it, actually we do c, right? Good to know the alphabet. C x squared cos x, and then we'll call it e x squared sine x. We want to take the derivatives and plug y sub p into our differential equation. So we're going to need the second derivative here. So whole lot of derivatives. Let's go ahead and work that out. Y p prime is going to be equal to, this is going to be a product rule. Tons of product rules coming here. So we're going to get an a cos x minus ax sine x plus b sine x plus b x cos x plus 2cx cos x minus c x squared sine x plus 2 ex sine x plus e x squared cos x. And now at this stage, it's kind of helpful, again, to combine our like terms before we take another derivative. We have a couple cosine terms here. Here's a cosine term, and here's a cosine term. Another cosine term here, and a cosine term there. So if we combine all of those coefficients, here's what we're going to get. We have a plus bx plus c 2cx plus ex squared cosine of x, and then the rest of it would be sine stuff. We have a negative ax we have a plus b, a 2ex, and then a negative cx squared. So plus 2ex. And I probably should have wrote it in standard form. It's close enough, but at least we got them all combined. So now let's go ahead and take our second derivative. So y double prime of p this is going to be equal to, again, we got a product rule coming here, derivative of the first times the second. So it's going to be the derivative of this thing here would be b plus 2c plus 2ex. Leave the cosine alone. And then derivative of cosine is going to be negative sine. Leave the first factor alone. And now this will be another product rule plus the derivative of the first part is going to be a negative a plus 2e minus 2cx sine x. And then plus, now leave the first part alone, derivative of sine will be cosine. So this would be a negative ax plus b plus 2ex minus cx squared cosine of x. And now we want to kind of combine the like terms, which will amount to combining their coefficients. So what are we going to have for the cosine's coefficient? Well, let's see. It's going to be these two right here. So let's see if we can combine those without having to do a ton of rewriting. So we have a negative ax we have a 2b's, so 2b's. We have two of those terms, so that's going to be plus 4ex. We also have a 2c. And let me switch those two terms around. So 2c plus, because I will go in order this time, 4ex. And now we get to the quadratic part of it, negative cx squared. That's all times the cosine of x. And now let's go ahead and combine the sine stuff. So if we try to combine our coefficients for sine, that would be these two here. And got to be very careful to note that there's really a negative sign out in front of that first parenthesis. So really we're going to end up with two negative a's. So negative 2a takes care of this and this. We have another constant term, which is this one right here, which is the 2e these two cancel. So a negative 2cx and a positive 2cx, those cancel. So this cancels with this. We have remember, excuse me, no, does not cancel. Take that back. Well, I just was telling about being careful a moment ago. They combine a negative 2cx and another negative 2cx will make a negative 4cx. We also have a negative bx. And then lastly, that'll be a negative ex squared. So let's go ahead now and try to combine this. So for our differential equation, when we plug it in, it's going to be y double prime plus y. So I'm going to be adding this to this one right here. So the first and last thing's what I need. So to save as much writing as I can, let me just kind of highlight. So it's y double prime plus y prime. Don't want that to visually distract us. So I'm going to add this function to this function. This is y double prime of p. when I do that, notice that this term, this is going to be a negative ax cosine, so that cancels. The cx squared will cancel with that one. And so what we're going to have essentially left over is we have this. We have 2b plus 2c plus 4ex times the cosine of x. Let's kind of come over now to the sine terms. If we add our sine terms together, this positive b sine x term will cancel with, which is essentially a negative b x sine x term, and then this thing here, which is a positive e x squared sine x, will cancel with that part here. So we have negative 2a plus 2e minus 4cx times the sine of x is equal to x cosine x minus cosine x. Which is what the right hand side is equal to. So I'm going to split this apart now one more time because we want to kind of match up cosine and x cosine terms here. So let's break this out a little bit. So we have a 2b plus 2c, that's a constant, times cosine x. And then we have this thing here, which is our 4e, which would be like an x cosine x term. And I'm going to do the same thing here, because we essentially have two different sine terms. There's a negative 2a plus 2e times the sine of x. And then there would be a negative 4c times an x sine x term, which is going to be equal to x cosine x minus cosine x. Okay. And now let's equate coefficients. So this coefficient has to match up with the coefficient of this one. And so that means that 2b plus 2c is going to be equal to 1. It also, oh, excuse me, yes, it's correct. No, negative 1. Sorry. This one here matches up with this guy here. So that should be equal to negative 1. This is our x cosine x term. This is our x cosine x term, and that should match up with positive 1. So 4e is equal to positive 1. And now for these two, there is no sine x or no x sine x term on the right-hand side. So essentially, both of those coefficients would be 0, which means that negative 2a plus 2e equals to 0. And in addition to that, negative 4c would be equal to 0. And now from here, we should be able to kind of go ahead and solve. This one here would imply that c equals to 0. This one here would imply that e equals to 1/4. If we plug c equals to 0 into the first one, we would have 2b plus 2 times 0 equals to negative 1. And that will imply that b equals to negative 1/2. And then lastly, if we plug e equals 1/4 into this third equation, we would have 2a plus 2 times 1/4 equals to 0. That is that negative 2a plus 1/2 equals to 0. So negative 2a would be equal to negative 1/2. Divide by negative 2, and we would get a equals to a positive 1/4. There it is. So we can now kind of go back and put it all together. So in all total, here's what we've come up with. So the entire solution, if you remember it, we had from our particular, should be from our complementary solution, we had this c1 cosine x plus this c2 sine of x that was already there. The a coefficient was the coefficient of our x cosine x term. So that's going to be a 1/4, so it's going to be plus 1/4 x cosine x. And then we had our b, which was our x sine x term. B was negative 1/2. So that's going to be minus 1/2 x sine x. C was our coefficient of the x squared cosine x term. So that was 0. So that term doesn't show up. And then E was the coefficient of the x squared sine x term. That was 1/4. So plus 1/4 x squared sine x. It's a pretty nice differential equation.